Okay, chapter 10 is thermal physics again. This is the HL portion of thermal physics. It's divided into three parts. The first part is about ideal gases and thermodynamics gas laws. Second part is the first law of thermodynamics, and the third one is second law of thermodynamics. Okay, so the first part is basically a continuation from where we left off in chapter 4. Where we left off was this, that the ideal gas, from the combining the three laws, Boyle's law, Charles' law and the pressure law, we get the ideal gas equation. Okay? This here is the ideal gas equation where P is the pressure, V is the volume, okay, N is the number of moles, R is the universal gas constant, and T is temperature in Kelvin. Okay? Now, this is called the equation of state or the ideal gas equation. Now, again, the universal gas constant here has approximately, this should be available information in the data booklet, 8.31 joules per mole per Kelvin. Okay. Now, ideal gases will obey this equation under all temperatures and pressures. So, if in the exam a student needs to define what an ideal gas is, an ideal gas can be defined as a gas which obeys the ideal gas equation at all temperatures and pressures. Okay. Real gases. Now, firstly, what's the difference between a real gas and an ideal gas? The significant difference is the intermolecular forces of attraction. So, real gases would behave like ideal gases and obey this equation approximately under conditions when the forces of attraction can be neglected. Those conditions would be high temperatures and low pressure. Okay, when there's low pressure, the molecules are spaced out far apart, and therefore the intermolecular forces of attraction are negligible. Now, next part is defining the concept of absolute zero. So if you plot the graph of temperature in degrees Celsius and volume for an ideal gas, you have something of this sort. Okay, so you have 0 degrees Celsius over here, and as the temperature increases, volume goes on increasing. Okay, so now if we extrapolate this, we reach a point here where theoretically the ideal gas will have 0 volume. Okay, this point is minus 273.16 degrees Celsius. This is called the point of absolute zero. Okay, it's the lowest possible temperature attainable. Well, theoretically attainable. Okay, and on the Kelvin scale, this point is 0 Kelvin. Okay, so this point here will be 273.16 Kelvin. Okay, and so on and so forth. So this is how the Kelvin scale and the Celsius scale are related. Then 10.1.4 is solving a few problems using the equation of state. So that's the first part. Then we move on to the first law of thermodynamics. Okay, 10.2 is to do with the first law of thermodynamics. Now, any gas, solid or liquid consists of internal energy. Okay? Now this internal energy comprises of random kinetic energy of the particles and also potential energy by virtue of the intermolecular forces of attraction. Okay? Now, the random KE of the particles determines the average random KE of each particle. Okay? And this microscopic quantity can be measured by a macroscopic property of temperature. So temperature is basically a measure of the average random KE of each particle. Okay? Now, the ways in which if I need to increase the internal energy of a system, there are two ways. Either I supply heat, okay, or I do work on the system. Basically, if let's say I have a gas and I do work on it, so without supplying heat, I can actually increase the internal energy of the system. Okay, so let's again, internal energy, you can never measure the absolute value of internal energy. All you can measure is a change in internal energy. So change in internal energy is defined as symbolized as delta U. Okay. Again, the heat supplied you would symbolize as delta Q. Okay. Now, work done on the system. So by definition, W means work done by the system. Okay. So this is by default definition that W is work done by the system. Now, if I had to write work done on the system, I would have to put a negative sign in front of it. Okay. So therefore, internal energy can be increased by either supplying heat or work done on the system. Now, when we are talking about an ideal gas, okay, we can completely ignore the potential energy part because there are no intermolecular forces of attraction in an ideal gas. Alright? So therefore, the internal energy is directly measured by the temperature. Okay? So if temperature increases, internal energy, which now is symbolized with delta U, will be positive. Okay? So the change in internal energy will be positive. If temperature decreases, delta U will be negative. Okay? And also vice versa. If delta U is positive, temperature has increased. If delta U is negative, temperature must have decreased. Okay? And by this equation here, we also have that the increase in internal energy is the heat supplied minus or add onto it the work done on the system. In other words, subtract away the work done by the system. Okay? So this here is basically the first law of thermodynamics. Okay? And if you think about it, it is nothing but another way of stating the law of conservation of energy. Okay? So now, let's talk more about work done on a system or by a system, basically. So let's say I have a cylinder, okay, and it has a moving piston, okay, and there's a gas inside this cylinder. So this moving piston, there will be a force exerted on this piston. Why? Each of these molecules are in constant random motion, and what happens is when these molecules hit the cylinder wall or the piston wall, they will change direction. Okay, a change in direction basically means a change in momentum, and we know that a change in momentum must be caused by an external force. if there was an external force applied on the molecules, by Newton's third law we know that an equal and opposite force must be exerted on the piston and the cylinder walls as well. Okay, but this force, by the way, force on walls of the cylinder is what causes pressure. Okay, the constant random motion of the molecules hitting the walls causes pressure in this container. Okay, so let's assume that the summation of the force of all the molecules hitting this piston of area A is F. Okay, and because of that force, this free moving piston moves to a point here. Okay, okay, and this point is, let's say, delta x away. So it has moved a distance of delta x. So the work done by the gas, okay, so this one is work done by the gas in moving the piston from here to here would be the force multiplied by the distance traveled. Okay, we also know that the pressure exerted by this gas on the cylinder walls is given by the force per unit area. So the force applied on this piston divided by the cross-sectional area of the piston. Okay, so I'll replace F here by P multiplied with A, okay, delta X. Now A delta X is this volume here. That's the increase in volume when this gas was expanding. Okay, so this will be P delta V. So the work done by the gas is P delta V. In other words, the pressure multiplied by the final volume minus the initial volume. Okay, so now from this we can understand that every time a gas expands, okay, it means there is work done by the gas, okay, which means that W is positive. Okay, and if a gas is compressed, which means there is work done on the gas, okay, because work is done on the gas at that time, and which would mean that W is negative, because W by definition, like we said, is work done by the gas. Okay, now